Sorry it took so long. Let's get going. Okay, first, basically treat it, the question may be, is the following balanced? Even if it didn't say that, if it just said balance it, you'd have to first of all find out if it is balanced, right? So we're going to start the same way either way. Generally, the question is not going to be simply, is it balanced? It's going to be, is it balanced, and if not, balance it. So looking at the elements involved on the left-hand side, carbon, hydrogen, and oxygen. Not shockingly. Joe. Reactants, products. Real quickly, just verify that those three elements are the only elements that make up the products. Carbons, yes. Oxygens, yes. Hydrogens and oxygens, yes. So we haven't created out of whole cloth, we haven't created new elements or lost elements in this process. What we don't know yet is whether or not the proportions of what is needed to make are correct. Right now, this formula would seem to say that one molecule and one molecule produce one molecule and one molecule. We know that may not be true. So this equation is generally true in the sense of this carbon-hydrogen chain reacts with oxygen to produce carbon dioxide and water. Generally true, but we don't know how much of each is needed in order to make how much of each product. So now we're going to do the count, the atom count, remembering that we cannot lose or gain any elements. We have to have the same number of building blocks of the same type of building block on both sides of the reaction symbol. So with regard to carbons, from left to right on the reactant side, what am I going to write? Ray? What am I going to write? Yes. 1 by 5. Okay, so I've got one set of 5. The way I used to write it sometimes was 1 at 5. Okay, that's the way I would do it. Say one group at 5 per. But if you get away from that and just use the multiplication sign as one set of 5 or 1 per 5. One set of 5. The implied coefficient is here, right? One set of 5. So on this side, one set of 5. Any other carbons? No. So hydrogens. 1 by 12. Okay? One set of 12. Any other hydrogens? No. Oxygens. 1 by 2. One set of 2. So we've got a total of 5, 12, and 2 on the reactant side. Now let's consider the products. Carbon, from left to right. It appears one time, so all of my carbon is right there. My carbon is one set of 1. My hydrogens, they only appear in this molecule, the water molecule. I have one set of 2 for a total of 2. Oxygens are split now. They appear in both molecules, 2 places, here and here. So I look to the coefficient is an implied 1. For this oxygen, it's one set of 2. So it's 1 by 2 plus this molecule. The coefficient is implied 1. 1 by one set of implied 1. One set of 1. For a total of 3. Okay, I haven't done this one yet, so we're checking each other, right? I'm walking through it, but I make mistakes. So keep checking me. All right. So, what am I going to ask myself now? Okay, is it balanced? No. First one, if we're going down 5 and 1, no. And in order for it to be balanced, every one of them has to be balanced. Each element. Carbon's not balanced, hydrogen's not balanced, oxygen is not balanced, none of them are balanced. The equation is obviously not balanced. Then you ask yourself another question. Yeah, where am I lacking? Which do I need more of? In carbons, I need more carbons in the product side. Hydrogens, I need more hydrogen on the product side. And oxygens, I need more oxygens on the reactant side. And I gave you a hint yesterday about the order of doing things. What was that hint I gave you? If you look to your equation and you find an elemental form, okay, in this case the O2, right? What was that hint? Save it for last. If it involves an elemental form, save it for last. Well, here it's the oxygen on the reactant side. So if I need more on the reactant side, I'm going to do that last. Why? Because if I need more on the reaction side, all I need to do is mess with this coefficient, and there are no other atoms in that molecule that get switched around. It's only going to affect oxygen. If I change a coefficient over here, I'm now messing with both carbon and hydrogen. If I change it here or here, I'm messing with carbons and hydrogens. But if I'm messing with it here, it only affects the oxygen. So save it for last. It's kind of like, that's the wild card at the end. You clean up the deck. You clean up the hand, okay? So save it for the end. So ask yourself the question, where do I need more of? Pick one of the other two, or in this case two, carbons or hydrogens. Okay, Savannah, pick one. Carbon. Okay, so how am I going to get 5 carbons on the, or at least 5, or get more, let's put it that way. How am I going to get more carbons on the product side? Okay, in front of the carbon dioxide? Good. If I put 5 in front of the carbon dioxide, now recognize that this coefficient here is both in carbons and oxygens. So it's going to affect carbons and oxygens, these two, top and bottom. I've just changed it from one set of 1 for carbon to 5 sets of 1 for carbon, and I now have 5. And in the oxygens, I've gone from one set of 2 oxygens to 5 sets of 2 oxygens, which now gives me 11. Okay? We good so far? You guys agree with me? Again, make sure I didn't make a mistake. Now, oh, and one of the other hints too is when you choose anything to increase, try to do it where it's the only time it occurs on that side of the arrow sign, on the reaction side. Like in this case, hydrogen. Hydrogen only, we need more hydrogen on the product side. And notice that the hydrogen only shows up in one molecule. That'll be better for you. Save the elementals for last, and do those that occur in only one element or one molecule first. That tends to work best. So in any case, we were looking at it now. We're saving this for last, so this leaves hydrogen. We need to increase hydrogen on the product side, right? So Bethany, how are we going to do that? Okay, so if we know we need to increase hydrogen and on this side, and the only place it occurs is in this molecule, so this has to be the key. We're hoping to get 12. We currently have 2 because we have one set of 2. It would be great if we could somehow get 6 sets of 2 so that we could have 12, right? But that also, again, messes with our oxygen. So oxygen down here, rather than having one set of 1, we now have 6 sets of 1 for a total of 16. Okay? Carbons, balanced. Hydrogens, balanced. Oxygens, I need more on the reactant side, and it's in its elemental form. And that means we can adjust this, and it doesn't mess up our carbons and our hydrogens. You see that? If you save it to the end, it doesn't mess up anything else. So you get to this point and say, I have 16 on the product side. I need to have 14 more, or think of it as 16 total on the reactant side. How am I going to get 16 from it only occurs here in sets of 2? How many sets of 2 do I need in order to have 16? 8. So when I change that to 8, it changes this to 8, means that I have 16, balanced, balanced, balanced. The whole thing is balanced. So C5H12 plus 8 oxygen molecules reacts to produce 5 carbon dioxide molecules and 6 water molecules. Which is different than, right? That is why, folks, Mr. Baker tends to cross his zeros, because I don't see a 0 there. That's an O. If it were 0, it would look like that. See? That's why I do what I do. That's why sometimes you get a quiz and it's not clear what I'm asking. It's because I used a font, for example, that doesn't put a little hook on the bottom of an L, or you see letters that aren't technically there, or capital I's that some fonts just have it as a straight bar. It looks like a lowercase l, as opposed to having a top and bottom. So that's where the font you use for different courses is important. There are some fonts I can't use in chemistry because it doesn't show the letters correctly in a way that you can understand it. If I was looking at a molecule that had carbons and iodine in it, as opposed to if one font might make it look like I'm asking you about chlorine instead of carbon and iodine. So, any questions on this on your own? Okay. Now there are other answers to the on your owns, 6.9 and 6.10, and I'll let you go ahead and work those. Let's just read through the word problem, however. Make sure we can set up the problems, that you understand how to set it up, and then I'll let you work it on your own. Not right now. We're going to do some extra practice problems in a minute to practice this process. But I'm going to read on page 232, if you care to look. There's the on your owns. And the first one says, hydrogen, oh, we did this one yesterday. Hydrogen and oxygen react violently to make water. Write the balanced chemical equation for this reaction. So what's so hard about hydrogen and oxygen reacting to produce water? Okay. Hydrogen and oxygen reacting to produce water. But what is key? Why is this wrong? Hydrogen and oxygen reacting to produce water. Okay, it's not balanced. That's true, it's not balanced. But okay, keep going. Shouldn't this be an H2 as well? Isn't hydrogen a polyatomic ion? Uh-huh. We don't find elemental hydrogen as a single H. It's H2 molecules, and oxygen as O2 molecules. So this is one where reading the word problem says, hydrogen and oxygen react violently to make water. Write a balanced chemical equation for this reaction. This is a equation. It's not balanced yet. But to even start to do it, you'd have to remember, oh, it's not H, it's H2. Oh, it's not O, it's O2. Because this is the way they appear in their elemental forms. They appear as molecules because they're homonuclear diatomics. Reacts to produce H2O. And remember, when you get to this side, it's not H2 because it's a homonuclear diatomic. Once they start forming molecules, those bonds are being broken and they're being reconfigured. This is an H2 because oxygen has 6 valence shell electrons and needs to share 2, and it shares 1 from each of the hydrogens. That's why it's H2, not because hydrogen is a homonuclear diatomic. Okay? That's the difference. I think we had this on the board yesterday and we stopped with it on the board. Some of you had some questions afterwards, so let me finish this one at least. That'll leave one other on your own that we haven't talked through. If we were to go through and balance this one, it would be pretty straightforward. There's no carbon, but we've got a HO, not a CHO, right? Watch it. Okay? So reactants and products. Let's look at what we have here. How many hydrogens? We've got one set of 2. And oxygens, we have one set of 2. And for water, hydrogens, we've got one set of 2. And for oxygen here, we have one set of 1 is equals 1, right? Now, how do we get it to be balanced? What are we lacking? Well, oxygen product. How are we going to get what we need 2, right? How are we going to get that? Put a 2 in the front. Coefficient of 2. Now we have 2 times 1, which is equal to 2, but unfortunately, now we have 2 times 2 hydrogens, which gives us 4. We need 4. What are we lacking? Hydrogen on the reactant side. Here's our hydrogen. How do we get it? 2. 2 times 2? 4. And now we're balanced. Now, there is a way, there is another way to do this. You'll end up with the same answer, okay? Like I said, this is kind of like math where there's multiple steps, different routes you could take to get to the same answer, as long as each step you do is valid, it'll work. Let's go back. Okay, so this is the preferred way. This is more of, and this isn't a slam. This is just where we are, right? This is more of a novice way of doing it. It's very straightforward. Keep adding the way we've been doing it, right? That's the process. There is another process which will sometimes be quicker, but what does quicker also mean? Risky, okay? So until you truly understand it, this might be a little riskier, but hey, if you're one of those daredevils that does 80 Dinn-Dixie, there should be no problem, okay? So here we go. Let's back this up a little bit, and we'll look at it in a quicker but riskier way. I'll find a broken roller coaster somewhere. You can have fun on your own and kill yourself. Just don't take my daughters with you, okay? Or your yeah, but thanks, Will. It just seems more effective if I talk about the daughters. But yeah, you're right. I'm not exactly offering you up, okay? So yeah, okay, good. All right. So is this good? I did it real quick. 1 of 2, 1 of 2, 1 of 2, and 1 of 1. Okay. So we look at this, and when I look at this now, I say, what do I need? Well, we said before, are we going to be able to do it with oxygen? Yeah. You kind of work it the opposite way. When I ask the question, and I prefer you to start with asking the question, where am I lacking and how do I get more? Okay? There's another way you can go about it and say, where do I have too much and how can I get less? It's the same question, just in reverse, like going from the other way, right? If I ask the question, where do I have too much and how do I get less from what I see on the board, what would I do? I've got too much of what? I've got too much of oxygen, right? How do I get less? Now, okay, 1/2. 1/2 of 2 gives me 1, and now you see it's all balanced, right? But there's another step. This is a little quicker, riskier, right? I can reduce by cutting the coefficients, and let's say that before was a coefficient that when I divided it in half, it gave me another whole number. I'd be done. Take half, let's say that it was 2, I take a half of it and I've got 1. I'm done. But when you do it, when you divide by, in this case, divide it in half, when your coefficient ends up being fractional, you cannot have a fractional coefficient. Okay? You can't have, in your final answer, you cannot have a fractional coefficient. So this is a partially done problem. 1 hydrogen and a half of an oxygen produces 1 water. But since I cannot have a half, how do I convert the half into a whole? I need to multiply this by 2. I'm going to multiply it by the reciprocal, right? Anything times its reciprocal is going to be 1. I've got 1/2. If I multiply it by 2, that will make this a 1. If I multiply it by 2, it now is a 1, and it's implied 1 there. But I have to multiply everything by 2. So here's the way I had it originally. The way I would write it again now is if I multiply every coefficient by 2, be 2H2 plus O2 produces 2H2O. See? I had a half, 1, a half, and 1. I cannot have a fraction, so I need to get rid of the fraction by multiplying it by 2, and the only valid way to do that is to multiply every coefficient by that number, 2. So I multiply 1 by 2 to get 2, a half by 2 to get 1, and 1 by 2 to get 2. You get the same answer, but again, it's a little bit riskier. But it may work for you. Again, if you don't do that and you simply go by where do I need more of and how can I get it? But at the end, you need to ask yourself this question as well. Once you have it balanced, then you need to go through and look at all of the coefficients and say, can I reduce them? So if I had, for example, 2H2O plus 2O2 produces 2H2O, hopefully you see that 2 plus 2 produces 2 could also be written as 1 plus 1 produces 1. That tends not to happen when you build it this way, but you need to do that as your final check. Hey, can I reduce all of them? What is the greatest common factor for all the coefficients that'll still give me a whole number? So it's kind of like the empirical formulas we did before. If there's 2 of these and 2 of these and 2 of these, oh, I could really make it 1 and 1 produces 1, or 3 and 3 produces 3. I need to simplify it. Simplify it down, but do not take any of them to be fractions. They have to be whole numbers, whole integer numbers. Let's flip forward to some EPPs. Just check yourself. Just go through and say, do I have any fractionals? No. Okay. Do I have any multiples? Can I reduce them? No. Okay, then I'm done. All the way to the appendices. Yep. We're going back to 620, EPPs for Module 6. And again, I didn't have a chance this morning. Not excuses, just the fact, because I got called into that meeting. I will come up with your homework. We need to knock out some homework on this module and test this module and hopefully not have it, because we only have like 2.5 more weeks. Well, 1.5 more weeks of classes and then fun week, right? Yeah, fun week. Midterms. It's fun week. I'm not deceiving you. Testing is fun. You don't think so? It would be if you knew the material. It's another opportunity in which to excel. Yeah, okay, see, it works. Or as we say in the Marine Corps, live to fight another day. It's a good day. All right. There are 7 balancing problems for Module 6 on 620. 1 through 6. Emily, what 1 through 6? Just give me a number. I don't have a preference right now. Just pick. Even if you don't have not even by looking at it, just give me a number 1 through 6. Just choose one. 3, which would be number 9. Yeah, because there's actually 7. So number 9, balance the following equation. I'm going to take the book with me here. AgClAq plus Zn reacts to produce ZnCl2 AQ plus AgS. This is one of my most favorite reactions. I didn't recognize it till I started writing. It's like an old friend. Like, oh yeah, I remember you. Okay, who wants to tell me what this reaction says? Just put it in layman's terms, like plain stuff that your mama and papa would understand. Silver, chlorine, zinc. Okay, let's put it this way. Let's envision it. What are the different molecules we're looking at? What is the name of this one? Come on. What is this element right there? Ag. Silver, right, good, silver. It's silver, right? Because Au is gold, right? That makes sense. Au is gold, but Ag is not gold. Ugh, it's silver. So silver, which is a metal, and chlorine, which is a nonmetal, form a ionic molecule, which is known, since it's ionically named, it makes it silver chloride aqueous, which means I've got silver chloride mixed in water. right? So I have silver chloride in water, and I'm going to add to that some zinc, solid zinc, zinc powder, zinc pellets, something like that, solid zinc. So imagine this reaction in the laboratory is you have what appears to be a beaker of water, but mixed in it is silver chloride. Can you see the silver chloride? Depends upon the concentration. Maybe not. Maybe you can't see anything. But so you've got silver chloride, and you mix into it zinc. And I don't recall if this is a spontaneous reaction or not, but as you mix in, you're like making your cake batter, whisking under your arm. So here you're mixing the zinc chloride in water, mixing it up, and you drop in some silver chloride in water, and you drop in some solid zinc, let's say zinc powder, and a reaction takes place. You're magic, you know? And it's not like, watch, I can make the marker disappear. Okay, no, this is real magic. This is, okay, silver chloride in water, put zinc powder into it, something happens, abracadabra, and I now have zinc chloride suspended in water, and there's these things that I added zinc powder, and what do I get out the other end? Solid silver. So I trade, think of it this way, I've got this beaker with stuff in it, I sprinkle zinc, and it gives me silver. I'll make that trade all day long, wouldn't you? If you say, I'm going to take a salt shaker full of zinc, and I'm going to shake it in, and as I shake it in, it disappears, and then silver appears at the bottom of the beaker. And when I'm all done, I just scoop up the silver, melt it down, and go get my teeth fixed, right? Because you get stuff. No. Anyway, so you collect the silver. Okay, but think about that. Silver chloride in, and why is this a significant reaction for me? When I was a little bit younger than you are, I was in Explorers, Boy Scouts, they have these Explorer groups. And my father worked at Eastman Kodak, and so I got into the Explorer group at Eastman Kodak back when photography involved film with chemicals, right? Before digital. And they have this big building in Rochester, New York, where they process the film. And pictures, that the part of the chemical solution on film is a silver-based chemical. Film is expensive because it has a thin layer of silver and other chemicals on the film. And when you go and have your film processed so that you get the pictures back, part of that process is removing the extra silver. And so there was this huge room, a lot of fluids, a lot of stuff all over the place, these big tanks, and all this film running through it real high speed. And what they were doing was taking silver that was in solution, and as the current of this water went downstream, they had collectors there, electromagnetic collectors, that they would add chemicals to the silver in solution, and it would precipitate out. Precipitate is a word that means drop. Like basically, when you have rain, we call that precipitation. What's happening? The water vapor is turning to solid water, or it's not solid, liquid water. So going from gas to a liquid, and then because when it becomes a liquid, it gets dropped. We call that precipitation. So basically, in this process, it's raining silver. And Eastman Kodak had a collection process using electrodes, electronic system, that as this solid metal precipitated out, they would collect it. And so one of the jobs that we had was at the end, pulling out these large collectors of solid silver. It was kind of cool, to see that much silver, because at one end of the process, all you could see was what looked like water, and magically at the other end, silver appeared. And it was this kind of a process. They were precipitating out suspended silver and having it precipitate out into solid silver. Because in this reaction, zinc is cheap. Okay? Zinc is very cheap. But when you mix it in this solution, you gain silver at the end. If you don't precipitate it out and the silver stays aqueous, it goes down the drain. It's gone. So this kind of a reaction helps you collect all the silver before it goes down the drain. The question is now, is it balanced? Silver, chlorine, zinc. Do I have all of the elements in the reactant side? I do. Product side. Zinc, yes. Chlorine, yes. Silver, yes. So I have all of the elements. There's nothing on one side that's not on the other, so I can keep going. Let's start doing the counts for the reactants and the products. Silver. It only appears in this molecule. I have a coefficient of 1, one set of 1. Chlorine. Only this molecule. Coefficient of 1, one set of 1. Zinc. Only in this molecule. One set of 1. So I have 1, 1, and 1. Does everybody agree with me so far? Okay. And again, not because I'm right, just make sure I didn't make a mistake, because it happens more than you think. On the product side, silver. Silver occurs only in this molecule. Coefficient of 1, it's 1, and they come in sets of 1. One set of 1 equals 1. Chlorine. It's only in this molecule. Coefficient of 1, which means I have one set of subscript 2, one set of 2, which gives me 2. Zinc, only in this molecule, one set of 1. Am I balanced? No, not balanced. Ask the next question then. Where do I lack? Where do I need more of something? Chlorine on the reactant side. If I go to chlorine, it's in this molecule. I know now that if I mess with this molecule, I'm going to tamper with chlorine, but I'm also going to tamper with silver. So these two are going to change. In order to get what I need 2. I have 1, and chlorine is here in sets of 1. So how many do I need? 2 sets of 1. 2 sets of is my coefficient 2. That changes my chlorine here from 2 sets of 1, or 2 sets of 1, which give me 2. But it also changes my silver to 2 sets of 1, which give me 2. But we're good with that because I notice that as silver changes, I look on this side and I have silver in its elemental form, which means when I change this coefficient, I only change silver, which is sweet because I look at this and go, okay, balanced there, not balanced here. I need to increase my silver. Silver's in its elemental. This is a piece of cake because I need 2. They're in sets of 1, so I need 2 sets of 1. 2 sets of 1 gives me 2. And now 2, 2, 1, we're balanced. Okay? So 2 silver chloride molecules react with 1 solid zinc, 1 zinc molecule, because remember, the molecule doesn't know if it's solid or liquid. So 2 silver chlorides react with 1 zinc to produce 1 zinc chloride and 2 silvers. Doesn't create, produces, because we're just rearranging them. Creating is what alchemy was. Pre-chemistry, chemistry. Alchemy was, let's take a little bit of duck dung and a little bit of straw and a nail, and let's mix it together and see if we can make gold. Didn't work. Let's try something else. And just keep trying to mix things to create another thing. We don't do that in chemistry. The other thing is just a different combination of whatever we started with. Right? Hey, Rachel, why don't you pick another one? It'll be the last one we do today of the ones on that page. And if you don't have a preference, just give me numbers 1 through 7, not including 3. Number 6, second to the last one. Balance the following equation. Hey, Ray, tell me about iron. Tell me about that iron. What's its ionic charge? Iron's a transition metal, right? Does everybody understand my question? Okay, if I told you if it was sodium, was that Will? We need more information, but we can figure it out because I've given you the the final molecule. I've told you that this iron reacts with 3 chlorines. Each chlorine has a -1 charge. Therefore, this iron must have a +3 charge. Why? Because it matches up with 3 negatives to make a 1 neutral molecule. Chlorine, what's its ionic charge? Chlorine is a column 7 element, right? Column 7 element has a -1 charge, and I've got 3 of them. 3 chlorines, each one has -1. Okay? This iron has to offset those 3 negatives. How does it do it? By having a 3 positive charge. That's how we form ionic iron chloride, ferrous chloride. Okay, that was just a throwaway question to kind of refresh your memory on stuff we did a couple modules ago. But there's the equation. Let's balance it. Okay, and because of time, I would normally have you do this. I'm going to rush through it, okay, just so we can get it done. But hopefully follow and check me, because I make mistakes all the time. I see iron, chlorine, sodium, carbon, and oxygen. That's a weird looking O, but there we go. Okay? Now I'm going to go to this side and just double check to make sure that I am accounting for everything. We've got iron, yes. Carbon, yes. Oxygen, yes. Sodium, yes. Chlorine, yes. Okay? Reactants, products. Iron. Everything only occurs one time. See that? Okay. So iron, I've got 1 by 1. Chlorine, I've got 1 by 3. Sodium, I've got 1 by 2. Carbon, 1 by 1. And oxygen, 1 by 3. Products, iron, 1 by 2. Chlorine, over here it's 1 by 1. Sodium, here 1 by 1. Carbon, here 1 by 3. And oxygen, here 1 by 9. Is it balanced? No. Iron isn't balanced, so it can't be balanced. What do I need more of? What do I lack? Where do you want to start? Iron? Okay, so we need 2. We can get that by doing 2 irons. 2 irons here gives me 2, but it also messes with my chlorine. My chlorine was 1 set of 3. Now it's 2 sets of 3, and it's 6. What's next? Oh, okay. Yep, you're right. 2 sets of 1, 2 sets of 1. Part of that is just trying to go fast. So that's balanced now. Not balanced here. Give me another one then. Where do we want to balance? Chlorine product. Okay, we have 6. We need to have 6 over here. It only occurs here, right? So we're going to do that by changing the coefficient here to 6. 6 sodium chlorides. 6 sodium chlorides gives me 6 sodiums here, or excuse me, 6 chlorines. But it does also give me 6 by 1 sodiums. Okay? What's next? Where do I lack? Where do I need more?
Sodium reactant.
No, Tyler, which one? Sodium. Natrium. Right, sodium. Okay. So sodium. I need more sodium on my reactant side. It appears here in sets of 2. I need 6. How many sets of 2 do I need to get 6? 3. So I get a coefficient of 3. 3 times 2 is 6. That's my sodium. But it also messes with my carbon, which just becomes 3. And my oxygen, that becomes 3, and that becomes 9. And now it's 9, 3, 6, 6, 2. It's balanced.